Hi, I'm Mark Barsamian. In this video, I'll be discussing continuity. The reading for this video is from section 2.3 of the book, more specifically, just the beginning of that section, pages 118 through 121, including just one example, example 1. The homework that this video accompanies is homework 16, which is given a graph of a function, find limit and continuity behavior. So these problems. I want to start by recalling some examples that we did in the video for homework H02 involving finding limits for a function given by a graph. So here's the graph that we studied in those examples. Now, notice that that graph has holes, jumps, and points in the wrong places. There's a hole, there's a jump, there's a place where there's a point in the wrong place. Now these kinds of features, holes, jumps, and points in the wrong places, are easy to spot on a graph. But a reasonable question is there some way of analyzing the formula for a function to determine if its graph would have any holes and jumps? And the answer is yes. The concept of continuity will allow us to analyze the formula for a function and determine if and where its graph would have holes and jumps. Before seeing the definition of continuity, let's look again at that graph from the previous video and review how the accompanying table of questions was filled out, because we'll gain some insight into how continuity will be defined. So we had this whole table of cells to fill out pertaining to behavior of this graph at certain key x values. I'm going to go rather quickly through this table. You can see each row of the table corresponds to behavior of the graph near one of the key x values. And the rows are color-coded with the circles that I've drawn on the graph to show what region of the graph those rows are about. Some observations. First of all, at x equals -3, there is no break, no jump, and no point in the wrong place. So there, at that location on the graph, there's no funny stuff going on. Notice the following three things are all true. The limit as x approaches -3 exists, f of -3 exists, and the number that's the limit equals the number that's the y value. That is, this limit equals this y value. The limit equals the y value. Let's make some more observations. At all the x values where there is a break or a jump, one or more of those three things is not true. So for instance, at x equals -1, there is a jump in the graph here. Now notice, at x equals -1, the limit does not exist. The y value does exist, but there's no way that those two things can be equal because the limit does not exist. So the limit does not exist. The y value does exist, but the limit and the y value can't be equal because there is no limit. Now, what about at x equals 1? There's a hole in the graph. Let's go up and look at that here. There's a hole in the graph. Notice at x equals 1, the limit does exist. The y value does not exist. So there's no way that those two things can be equal because the y value does not exist. So the limit exists, the y value does not exist, and so those two things can't be equal. Let's go up and look around x equals 4. There's a hole in the graph and there's a dot in the wrong place. So this part of the graph. Notice that the limit does exist, the y value does exist, but they don't agree. The limit is 1, the y value is 2. The limit is 1, the y value is, here's a typo, this should say 2, and the limit and the y value are not equal. So in all three of these cases where there was a break or a hole or a dot in the wrong place, the limit and the y value are not equal, either because one or the other of them doesn't exist, or because they both exist but they're not equal. So after making those observations, we're in a good position to understand the following definition of continuity. We say these words: a function is continuous at x equals c, to mean this. The function f passes these three tests. The first test is the limit has to exist. The second test is the y value has to exist. And the third test is the value of the limit has to equal the value that's the y value. Now keep in mind that the first test is actually sort of a little mini three-part test of its own, because remember from before when we were computing limits, we thought of limits in terms of left and right limits. For a limit to exist, the left limit has to exist and the right limit has to exist, and those two one-sided limits have to agree. So we're going to do an example, and in this example you're going to be asked various questions about a graph, and some of the questions are about continuity, that's our new concept, but some of the questions are just simply about limits and about limits involving infinity. Those are old concepts from sections 2.1 and 2.2. All right, we're going to have, I think, 11 questions. Question 1 is, for each asymptote, give the line equation and say whether it's horizontal or vertical. Well, we can see that there's a horizontal asymptote here, and it's horizontal, so its line equation will be of the form y equals something or other. We have a horizontal asymptote, so its line equation is of the form y equals a number. It's the number 3. Y equals 3 is the equation for that red dotted line. And it's important to note that this is a horizontal asymptote on the left. Are there any other asymptotes? Well, yeah, there's an asymptote here. That's a vertical asymptote, and so its line equation is going to be of the form x equals some number. Well, this is x equals 2. And there's one more asymptote. There's an asymptote over here on the right. It has line equation y equals 1. And again, notice it's of the form y equals a constant because it's horizontal. All right, that's our first question. Before going on, notice that there are some other features that you might be tempted into saying are asymptotes, but they're not. So for instance, there's something going on here. There's a jump in the graph, but that's not an asymptote, not a vertical asymptote. There's a dot in the wrong place here, but that's not an asymptote. Let's go on to the next question. Find the limit as x goes to negative infinity of f of x. Well, that's related to the question that we just answered. In the question that we just answered, we found that there's a horizontal asymptote on the left with line equation y equals 3. That translates into this. This limit as x goes to negative infinity is 3. And remember that when you have a horizontal asymptote, the line equation y equals some number gives you a clue. That number that shows up in that line equation is equal to the number that's the value of the limit. Go on to question 3. The limit as x approaches negative 5. Let's consider the limit from the left. The limit is the number 3 because the graph is approaching the location negative 5, 3 from the left. Now let's consider the right limit. The limit as x approaches negative 5 from the right is the number 2, and that's because the graph is approaching the location xy equals negative 5, 2 from the right. Notice that number that's the value of the limit is the y coordinate of the location the graph is heading for. That happened in the previous limit as well. The number that's the value of the limit is equal to the y value of the location that the graph is heading for. Now notice, there is a dot in the graph at x equals -5, but that doesn't matter when we're talking about the limits. The limits are just about the trend. Where does the graph appear to be heading? So the limit from the left is a number because the graph appears to be heading for that location. The limit from the right exists, and it's a number because the graph appears to be heading for that location. So again, whether or not there's a dot at that location does not affect the limit. Now, what about the limit, though, the unrestricted limit, the two-sided limit? Well, we'd say that the limit does not exist because the left and right limits don't match. So the limit does not exist. Now let's consider the limit as x approaches -2. Well, we can answer this quickly. Notice that the graph is heading for the location xy equals -2, -1. That tells us that the limit exists and it's this number, -1. Now let's go on to the next question. Find the limit as x approaches 2 of f of x. Well, notice that at x equals 2, there is a vertical asymptote, and the graph goes up along both sides of that asymptote. So that tells us that the limit is infinity. Now notice a couple of things. First of all, the x arrow 2, that number 2, that tells us the x value that we're approaching on the graph. That corresponds to the line equation for the vertical asymptote being x equals 2. And the fact that the graph goes up along both sides of the asymptote corresponds to the fact that that limit is infinity. Let's go on to the next question. Find the limit as x approaches 6 of f of x. We'll notice that the graph is heading for a location on the graph. Heading for the location 6, 3. So I didn't say point because there's no point there, but there is a location there. That tells us that the value of the limit is the number 3. And again, notice that the y-coordinate of the location that the graph is heading for is the number that's the value of the limit. Let's go on to the next question. Find the limit as x goes to infinity of f of x. Now remember that limits at infinity, as x goes to plus infinity or negative infinity, refer to the end behavior of the graph. And we see this end behavior that there is a horizontal asymptote on the right. That asymptote has line equation y equals 1, so that tells us the value of this limit. So again, notice that the y-coordinate in that line equation, y equals 1, is the number that's the value of the limit as x goes to infinity. So far all these questions have been old ideas, limits and limits involving infinity from sections 2.1 and 2.2. Now some questions involving the new stuff, continuity. Is the function continuous at a equals -5? And if not, explain why not. Well, let's remember that there is a test that we have to consider for continuity. This three-part test. Let's go up and have a look. Here's the test for continuity. The function has to pass this three-part test. The first test is the limit has to exist. That's in itself a little three-part test. That's test 1. And then test 2 is the y value has to exist. And test 3 is the numbers from test 1 and test 2 have to agree. That is, the limit must equal the y value. Let's go back and look at our question now. So let's consider the test. The limit from the left exists, and it's the number 3. So I passed test 1A. What about test 1B? The limit from the right exists. It's the number 2. Again, remember, those are because the graph is heading for these locations. But test 1C is, do those left and right limits match? So we say that we fail test 1C. Let's go on and see if we would have passed any of the other tests. Notice that the y value does exist because there is a point on the graph at this location. What about test 3? Test 3 was, do the results of test 1 and test 2 match? Well, there's no way that the function can pass test 3 because there's no limit. So our conclusion is that the function is not continuous at x equals -5. Let's go on to the next question. Is the function continuous at a equals -2? And if not, explain why not. Well, notice that we can see that there is no break or jump in the graph at x equals -2. So we expect that we're going to find that the function is continuous, but let's do the test. The limit does exist. It's the number -1 because the graph is heading for this location, -2, -1. And again, notice the y-coordinate of the location the graph is heading for is equal to the number that's the limit. That's test 1. What's test 2? Test 2 is, does the y value exist? The y value is the number -1 because there's a point on the graph at -2, -1. Finally, question 3. Question 3 is, do the results of test 1 and test 2 match? So we see that the result of test 1 was the limit was the number -1. The result of test 2 was that the y value was -1. Those two things match. So our conclusion is the function is continuous at x equals -2. Let's go on to the next question. Is the function continuous at a equals -2? And if not, explain why not. Well, notice that at x equals -2, there is a vertical asymptote. Let's consider the test. So we already found that the limit as x approaches 2 of f of x was infinity. Now let's consider test 2. What about the y value? So the y value does not exist because there's no point on the graph at x equals 2. Now notice, you can't say the y value is infinity. There is no such thing. You say the y value equals a number to denote that there is a point on the graph with some x, y coordinates where y is a number. So the y value does not exist. So test 3, well, the function fails that. Now, here we say that the function fails test 3 because the results of test 1 and test 2 are not equal. Now, this is a little bit subtle, because what if you said in test 1, what if you said that the limit does not exist? Well, so then you'd have does not exist in test 1, does not exist in test 2. Could you say that those are equal? Does not exist equal does not exist? Well, no, the equal sign can only be used to equate numbers, real numbers. So even if the result of test 1 had been does not exist, you could not say that does not exist equals does not exist, because those aren't numbers. So we fail test 3, and so we say the function is not continuous at 2. Let's go on to our final question. Is the function continuous at a equals 6? And if not, explain why not. Well, let's go through the three-part test. So the limit is equal to the number 3 because the graph is heading for the location 6, 3. So again, as always, the y-coordinate of the location that it's going towards is the number that's the value of the limit. Test 2, what about the y value? So there's a point on the graph at the location xy equals 6, 2. So the y-coordinate of that location is the number that's the y value of the function. Now, what about test 3? Notice that the results of test 1 and test 2 don't match. So our conclusion is, since the function fails test 3, notice that the value of the limit does not equal the value of the y value. The function fails test 3, so the function is not continuous. That's the end of the example, and that's the end of the video. Thank you.